3 students. I think most of them will attend the 11 a.m. class. So you guys prefer to like come early and then kind of like have a longer break, right? That's better, right? So you guys have like a good sleeping habit, is it? Like you go to sleep maybe 11? No? Huh? Just wake up early, regardless of whether you got sleep or not. Actually, that's not very good. But then if you are young, you can kind of withstand the damage more than if you are older. So the reason is what? The reason is the reason you're forced to sleep late or you want to sleep late? Too many stuff to do. As in school stuff or what stuff? School stuff. I see. That's the usual case with engineering degree programs. Has been the way since many decades ago. Yeah. So usually we just kind of accept that. Yeah. So in any case, we wait for a bit first. Maybe 9:05, then we will start. Today I'm going to start on the new topic. Okay, so I pretty much finished the tutorial 5 already. Okay, except for the last question, there is the past year question. So I hope you can try that one out on your own first before, if you have any problems, you can check with me. And we are left with only 3 weeks, including today. So I'm only left with 2 topics. Today we will finish topic 6. Then we will left 2 weeks to cover topic 7. Hopefully I can finish. And maybe leave. We might do a consultation, maybe online, right, before the finals. So this semester, this trimester should be easier for you guys, right? Yep. Yep. The approach is, although there is okay, I cannot say that there's a standard approach, but there is a recommended approach, right? So if you look at the questions, usually you have to be able to derive the IVP, the governing equation, with the initial condition. And the derivation produces a certain kind of differential equation that you must be able to recognize what kind it is. That's the second requirement, right? The third requirement is based on what you have recognized, then you apply the appropriate solution method. That's the third requirement. So this is a recommended approach because there is no best approach, but there is a recommended approach for usual questions, but some questions can be out of the blue. So if the question is out of the blue, then you might need to apply some more unique approach. And this kind of things, you can only come with experience. Meaning to say, if you practice more, then you gain the better understanding and you get familiarity, then you are able to solve the question more effectively. So I can only make such a recommendation because the issue with problem solving, maybe in mathematics, is the questions can be kind of open-ended in terms of how you interpret it. So different engineers, when they see the same problem, they will interpret it differently. Some of them want like simplification so that they can use more simple tools to solve and analyze. Then some engineers, they want to have higher accuracy. Then they will include more subtle effects of the system, and then but they are okay with using more complicated methods to obtain the solution. So different engineers, they got different approaches. So therefore, there is no standard or best approach because it depends on what kind of engineer you are, and also what skill set do you know, and also the accuracy required of that problem. So in many cases, I can only say if you practice more you gain more experience and you gain more insight, and then you will be able to tackle the problems more effectively. Okay? So I hope I'm saying something and not saying nothing. Correct. You have to think about you have to understand, I always say this, you have to understand the physical meaning of the problem. So if you treat math as like, I give you one equation I ask you to solve, right? Then that's not a very good way. I mean, that's to me, that to me is the worst way to learn math. There is actually very good insights that you can gain from the mathematical representation. So if you master that kind of physical meaning behind the math problem, I feel it's going to be very beneficial in many areas of your work as well as your studies. Yeah, eventually, if you, by now you might have noticed that most of your subjects, even though they are different subjects, right, they all boil down to solving some math. Is that not right? They all boil down to solving some math, right? Not all, except the like soft skill subjects. So they usually they have some standard formula for you to use. Is it? You have to derive. Okay, okay. Oh, okay. Those on the digital electronic modules, right? Data structures, right? Yes, yes. Okay. So usually with computing, there are more algorithmic approaches to solve a problem. Okay, algorithmic approaches, right? Yeah, but in computer science and computing, actually, there's a lot of math involved, and you will experience that in Math 3 next trimester. Okay, you will be coding. You'll be coding like a machine learning neural network from scratch in Math 3. Yes, from scratch. From scratch. In Python, it's a one-liner or maybe five-liner. But in Math 3, you will code from scratch. That means you know exactly how it works behind the scenes. Okay? So, stay tuned. Right, so we are going to, yes. So we are going to start. Yeah, as I mentioned, I want to go through the mistake in quiz 2, which I made because I thought that ln t has no Laplace transform, which is incorrect. Okay, as highlighted to me by Javier, right? So ln t, so the deal with Laplace transform, if you recall the stuff that I have mentioned before it. So I mentioned that actually for Laplace transform, you need the area, right, to be finite. So you can see 1 over t I mentioned has no Laplace transform because there's an asymptote here. Okay, then like e to the t square also has no Laplace transform because this e to the t square is going to rise or increase much faster as compared to the decrease of e to the minus st. Because this one t square, so it's like super exponential. We call it super exponential, but this one is only exponential. So certainly the super exponential is going to win, okay, because it's more super. So therefore, if there's an asymptote at t equals to 0 or like anywhere within 0 to some finite value of t, then actually there will be no Laplace transform, generally. Okay, so I overlooked that for ln t, actually there is a Laplace transform. So why is it that ln t has a Laplace transform? It's because the area underneath ln t is finite. So actually ln t looks like that, right? This is a ln function. Okay, so this ln t, this t. So you can see that there is an asymptote at t equals to 0. Okay, but however, this area, interestingly, is actually defined, is convergent, meaning to say there's a finite area here. Then how that turns out to be is because, right, this, when it goes to minus infinity, it goes to minus infinity too slow. So this part, right, actually approaches minus infinity slowly. So of course the word slowly is like ambiguous. What do we mean by slowly? So actually if you were to integrate 0 to, let's say, 1, okay, let's say this is 1, okay, because we are concerned about the area here. If you integrate 0 to 1 for ln t dt, right? Actually, we have gone through this in Math 1 before, and the answer you get is actually t ln t minus t. Then you integrate from this one 0 to 1. Okay? So if you look at, you put in 1, it's no problem, because you put in 1, right, this guy is going to give you 0. Right? Because you put in 1, right, 1 times ln 1 is 0, so it's 0 minus 1, then minus. Then if you put in 0, then you get 0 ln 0. So this one is like 0 ln 0 minus 0. Okay, you sub in 0. So if you look at this 0 ln 0, 0 is of course 0. Ln 0 is actually minus infinity. This part, can see, ln 0 is minus infinity. Okay, now the issue comes. 0 times minus infinity. So the question is it defined or not? The answer is, it is defined. This is an indeterminate form. This guy is indeterminate, right? Because if you take the limit as t approaches 0 on t ln t, this guy, if you go and evaluate this limit, for example, using your L'Hopital, you will realize that there is a limit. Okay, the limit is finite. So this limit is L. Okay, it's not infinity or it's not undefined. So therefore, if this is defined, that means this is some value L. This is some value L, right? So therefore, L is a number. Then if you work out the resultant, right, it will be minus 1 minus L, for example. So therefore, there is indeed an area here, a finite area. So hence, the Laplace transform is defined because the area is finite. Okay? So because of this mistake, right, I thought that ln t has no Laplace transform. So therefore, I have awarded everyone the mark. Okay? The answer is supposed to be this. 1 over t plus 1 whole thing square. Because this is like 1 over t square, but when t becomes t plus 1, that means you shift the entire 1 over t square curve, right, to the left by 1. So therefore, there is actually no asymptote for this function from 0 to infinity. Okay? So if you plot, you will see, like for example, if you were to plot 1 over t plus 1 square, 1 over, okay, let's make it x plus 1. So you can see that the Laplace transform is only defined from 0 onwards. The area, right, from 0 onwards, after you multiply this by e to the minus st. Okay, but just from this, you can see that the area here is actually bounded. So therefore, it is going to have a Laplace transform, even though it has an asymptote, but that's outside the interval 0 to infinity. Okay, so by right, it will be this answer, right? But ln t, as I mentioned, since it also has a Laplace transform, so maybe some of the students get confused. So therefore, I will give the mark to everyone for this question. Okay? Happy? You know what's the option that most of you chose? No, option 1. Most of you chose option 1, t to the minus 3. Most. So most of you got a free mark, right? Thanks to Javier. Most of you chose this, but this is 1 over t cubed, what? 1 over t cubed is like 1 over x cubed. See? So the asymptote is here. So this area cannot be finite. Okay? Yeah, so that's the mistake that I want to clarify. So today we are going to start on topic 6, right, which is systems of linear first order ODEs. So the key word here is system. But the system here does not represent the system that we have been saying previously. It is more about set of linear first order ODEs. So what we mean by set is, instead of one ODE, you get more than one ODEs that are what we call coupled, as you will see in a bit. So this is going back to topic 3. So topic 3 here, right? if you recall, we analyzed or we modeled the cooling process of this steel plate. Okay, and then we did mention something. We say that, oh, the steel plate is losing heat to the surrounding air, for example. So the air is the cooling medium. Okay, of course, the cooling medium can be anything. So when you use airflow to cool this medium, right, we are assuming that this surrounding temperature Ts, which is for the air, remains constant. Okay, so Ts is not changing, it's a parameter value. Like for example, if you put in an aircon room, right, let's say 24 degrees Celsius, then that will be 24 degrees Celsius throughout the cooling process. Then we also mentioned that through an experiment, right, if you recall topic 3, right, there's an experiment that the experimental data deviates away from the theoretical solution towards larger values of time. Okay, as time progresses, right, you notice that actually the cooling less effective as compared to what is shown analytically. Okay, and what's the reason? Then one of you mentioned that the air is actually heated up, and that's absolutely correct. Okay, so the reality is this Ts, the surrounding air temperature, logically cannot remain constant, what? Right? Because it is going to remove the heat from the heated object, and therefore its temperature must rise. Okay? Right? We must respect the heat transfer. We must respect the conservation of energy. So, what happens to the ODE when you have Ts also changing? That's the big question. Okay, so what happens to this ODE that you are trying to solve, right, for the temperature of the steel plate when you have the other side of the story, right, that is the medium also changing in temperature? Okay, so of course, is this model so-called wrong or not? If let's say your Ts is changing and then you assume Ts to be constant, okay, so of course this model can still be applied if you have a very large airflow. That means, meaning to say, you have a very large volume of airflow across that particular object, and usually the speed must be quite fast. Okay? The speed must be quite fast. That means the object, the hot object, right, is small as compared to the entire surroundings, and you have the air moving very fast, so much so that, right, the air does not heat up substantially before it passes, after it passes the heated object. Okay, so if that is the case, then you can treat Ts as relatively constant and your temperature function will still be accurate. So let's consider the case when you have, for example, the air that is inside a room. Okay, so if the air is inside the room and the air is not like of a very large volume as compared to the heated object, right, then you are assured that this air is going to get heated up already. Okay, so how do we address it? Well, we just apply the same conservation of energy, because air can be treated as another object, right, that is receiving the heat from the plate. So in topic 3, we applied conservation of energy to the plate, right? Then in this case, we can of course apply the same thing to the air as well, right, or to the other body, right, whatever the plate is interacting with. So now if you look at the conservation of energy, so by now you should be quite familiar with it already, right? You still have your Q in minus Q out equals to change of energy within the plate. Then the Q in must be UA TP minus TA, right? For example, the TP here, right, represents the temperature of the plate. TA here represents the temperature of the air. Okay, and you notice that this is in the Q in term. Q out is 0 because for the air, right, it is receiving the heat lost from the plate. Get it? So therefore, the right hand side is just M air C air T prime air. Okay, so it's the same term, but I added the subscript A because just to differentiate that they are for the air. So now if you rearrange this ODE, right, you're going to get this form. Okay, it's the same form as that for the plate. So TA prime equals to minus RA, where RA is UA over MACA, then multiply by the temperature difference. Okay, so therefore if you put this ODE for the air together with the ODE for the plate, because each of them comes from a conservation of energy, okay, from their own perspective. So you notice that temperature of the plate must be decreasing because of this negative term, okay, because rate of change, the temperature rate of change is negative. So the temperature of the plate must be decreasing, makes sense, okay, hot becomes cooler. But for the temperature of the air, it must be increasing, okay, because this term is positive. On the right side, right, is a positive term. So therefore, rate of change being positive means temperature must increase. Yes? Yep. Very good. Exactly. So the steady state, as you will see later on, the steady state temperature for both bodies will be the same temperature in the middle of the initial temperatures of the air and the plate. Make sense, right? Okay? Because once it's get heated up, the colder one get heated up, the hotter one get cooled down. So eventually they settle at some same or some uniform temperature, right? That is in between. Okay? Makes sense, huh? So this is what we call a coupled ODE. Coupled ODE, as the name suggests, coupled. Okay? So why is it coupled? What do you mean by coupled? So notice that the rate of change of the temperature of the plate is dependent on the temperature of the plate itself, but also dependent on the temperature of the air. And the same goes for the rate of change of temperature for the air. Okay? So the rate of change is dependent on the plate's temperature and the air's temperatures as well. So therefore, you notice that both are related to both temperatures. Both rate of changes are related to both temperatures. So they are coupled, which means you cannot say you solve one by one, you know. You cannot solve one by one. You have to solve together as a system. So this is what the system here represents. Can Okay? So therefore, this is analogous to a couple, right? Like for example, you with your girlfriend or boyfriend, you are couple. Okay? Because whatever you do, right, will affect your significant other as well as the other way around. Okay? Vice versa. Right? So therefore, this is what we call a coupled system. Okay, and there are many coupled systems of ODEs that are kind of famous or applicable, right, in the real world. Okay, that means we have to solve together. So in matrix notation, so whenever you have like a system of equations, right, you can actually write down it as a matrix equation. So you can see I put the prime terms in the vector. So TP prime and TA prime put in the vector. Then you can see that the right hand side, right, there is TP and TA. So I put it in that same order as the prime term. So TP prime, TA prime, that means I'll put TP, TA. Of course, you can invert. Okay, that means you want to put TA first, then TP later, is up to you. Okay, but it's just that your matrix A will be slightly different from mine. So if you put in this order, then you notice that actually the matrix A here, right, will be just the coefficients Rp and Ra respectively. So you look at the first term, this one is what? Minus Rp times Tp. So minus Rp times Tp will be minus Rp times Tp. Then this is plus Rp, right, times Ta, because minus times minus. So you can see the positive Rp here. Can Okay? So which means to say that, right, this is our equation 1. So let's say this is our row 1. So the row 1 will be here times here. Then this is our row 2. So row 2 will be this times this. Okay? So of course the standard matrix multiplication rules apply. So therefore, we are now going to solve this matrix equation problem in terms of an ODE. Okay, it's a differential equation because in vector form, right, we have t prime equals to AT. Okay, and t in this case, they are vectors and A is a constant matrix. So therefore, this is not new. So this is what a general system of first order ODEs will look like. Okay, so you can see so it's possible that you have n coupled ODEs, x1 prime to xn prime. And you can put in the linear form, as you can see, right? It's a linear combination. Each rate of change, right, is a linear combination of the other function terms. And you can also be inhomogeneous because you have an excitation. So the f of t, this guy, are the excitation terms. So we'll deal with the excitations later on. Whenever you see excitation, it is Duhamels, because Duhamels is the guy that gets excited. Okay? So therefore, if you put this in a matrix form, right, this is what you get. So once again, you get the inhomogeneous first order ODE, x prime equals to a of t x plus f of t. Okay? Where the f of t will refer to the excitation vector. Is that right? So now we are going to simplify and look at just when f of t equals to 0, which means that it is homogeneous. Okay, we deal with the homogeneous system first. And then we have all the coefficients being constants. Okay, so they are no longer functions of the time or any independent variable, right? We just say that they are constants. So therefore, we are solving x prime equals to ax. Then the initial condition given at t equals to 0 will be x naught. Okay, so we put everything as quite general. So then the separation of variables tells us that the particular solution is e to the at x naught. So this is something that we already know how to solve using separation of variables. Okay, which we are just going to quickly recap. Because this one topic 3, so now topic 6, right? Maybe forgot most of it already. So therefore, let's go through this quickly together. Okay, so this x prime equals to ax, right? You use separation of variables. So therefore, this is actually dx dt, yeah? Okay, so x prime is really just dx dt equals to ax. So therefore, if you use separation of variables, you're going to get like 1 over x dx equals to equals to a dt. So therefore, separated variables, so you integrate both sides, right? So then you get ln of x equals to at plus c. C is a constant. So then you exponentiate both sides, right? The usual stuff. So then you get x, the vector, equals to e to the at plus c. Okay? So this guy is e to the at times some maybe c1. Okay, and in this case, because your, let me see this. So this is a vector, and this is a matrix, right? So therefore, C1 in this case should be a vector. Okay, so this C1 must be a vector because vector equals to vector. Can So, oh, I forgot my modular sign here. Let me just add it in. So then after that, if you apply the initial condition, then you're going to get your C1 vector. So apply initial condition will be the vector at t equals to 0 will be e to the 0 times the C1 vector. Then this guy must be x naught vector. So it shows that C1 must be x naught then. So C1, the vector, must be x naught. So therefore, your particular solution, x of t, will be hence e to the at times x naught. Because C1 is just x naught. So this will be your particular solution. Is that alright? So I think you might find this familiar because we just went through this in topic 3. That's before your term break. And notice that I cannot anyhow move the x naught to the front because e to the at, a is a matrix. So e to the at is a matrix. Then matrix times vector. Then you get the vector here. Okay, certainly you can move x naught to the front if you convert the column vector here into a row vector. Okay, but I think we just keep it in the same order because matrix multiplication is not commutative. Any questions? Good. So, what's the deal? The deal is that actually the solution is easy peasy. It's really something that we have seen multiple times. It's just this guy. Okay? However, The issue is the solution depends on the exponentiation of a matrix A, right? But we already dealt with that already, what? In topic 2, we learned all the eigen decomposition as well as the Jordan decomposition methods, right? And then we already stated through the Maclaurin's or Taylor series, how do you write down the function, the general function of a matrix. Okay? So therefore, if you have the matrix A able to be diagonalized, then you perform eigen decomposition. Okay? Perform eigen decomposition already. Write down e to the at, just using your p e to the dt, p inverse. Okay? So effectively, just applying the exponential function to the diagonalized form at the diagonal elements of the diagonal matrix. Okay? So, yes. No. So let me write down. Okay, so therefore this thing is just x of t, right? Equals to e to the at times x naught. Then this guy e to the at, because your a is in PDP inverse, right? You have to be like that. So therefore, but t is a scalar. Because time t what? So it's just in, for example, seconds is a scalar. So it's a scalar multiplication to a matrix, which means to say that you have p e to the dt, then p inverse, then times x naught. D is a diagonal matrix, right? Then this t, right, is just a scalar. So scalar you multiply to the diagonal matrix, you are just going to get the eigenvalues multiplied to t. So effectively is p times e to the lambda 1t, then e to the lambda 2t. Let's say you have lambda 1 and lambda 2. So for example, a 2 by 2 system. Then the off diagonals will be clearly 0. Then the p inverse. Then you times x naught, the vector. Is that right? Yes. Which part? P and p inverse. Oh, you are saying that, why is it not like e to the p d p inverse, right? It is. It is. There. It's all derived here. So you can see that, right? E to the PDP inverse is correct. Okay, but if you were to use the Maclaurin series or Taylor series, e to the a is I plus a squared 2 factorial, blah, 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 right? So therefore, if you apply the PDP inverse to the matrix A here, so this is just a power series, right? And if you put it A equals to PDP inverse, then A to the n, right, is just D to the n. That means lambda 1 to the n, lambda 2 to the n, etc. Okay? Then you notice that in this sum, the P can factorize out. The P inverse can factorize out. So you have just this sum of D to the n over n factorial here. This guy is exactly e to the d. So through this Maclaurin series, which is making use of the power series, you can factorize out the p and p inverse, right, outside of whatever function being applied. This t, right, you have to stick to the d, because at, right, the t must multiply to d. Is that right? Okay, so of course your reasoning can be right. The t can multiply to p or p inverse also. Actually can also. So actually can also. It's just that after you multiply out, right, it is still giving you the same answer. Okay, so it makes sense. Okay, so you can multiply to any of the terms, because by right at, right, is pdp inverse. PDP inverse times t ma, correct or not? So therefore, you can jolly well, right, apply the t to any of the terms here. But it makes sense to multiply t to the d. Why? Because d is a diagonal matrix. So actually, you only multiply to the diagonal elements instead of multiplying to all the elements inside p or p inverse. So it's like less work lah. Can? Okay, good. So I hope this clarifies your questions. Okay, so basically this is the answer, right? This is the answer. So all we need, right, are the eigenvalues lambda and the eigenvectors that form your matrices P and P inverse. Okay, which is actually being given here, as you can see. Right? So hence, if your matrix A is a 2 by 2 matrix, and in your course here, we will only consider 2 by 2. Okay, certainly the diagonalization and the solution form can be extended to systems of 3 equations or more. Okay, but we're just going to keep things simple and stick to 2 by 2 at maximum. So therefore, you can see that because the matrix P, right, is a concatenation of the eigenvectors. So just put V1, V2. Then certainly, if your diagonal matrix D, if you have this as V1, V2, then your diagonal matrix D will be lambda 1, lambda 2. Okay, so therefore e to the dt, as I mentioned earlier, will be the terms here. Then P inverse, I just go and invert your matrix P, and x0 is your initial condition vector. Okay, because you got x1 not and x2 not, what? Yep, yeah. No. T is a scalar variable. So because your function is a function of t, so t is changing, like time is changing. So you want to know what is the solution, right? Or like the temperature functions with respect to time. So at different times you have different temperatures. No, it will be a function of time. This thing eventually will be a function of time. Okay, so later on you will see the actual function of time, and we can plot it out. So certainly, some matrices A cannot be factorized, cannot be diagonalized. So therefore, we have to use Jordan decomposition. Okay, so as you can see, because Jordan decomposition, there's a 1 at the top right. So we have to be able to handle that. Okay, but we already know how to handle that already, because whatever function you do to the diagonal elements, right, the top right is just the derivative. Okay, that means you differentiate with respect to lambda. So therefore, this is something that we have already derived in topic 2. So you can see that if you have a matrix A that is defective, then you are going to use Jordan decomposition instead. So e to the dt, because you don't have d, so you use e to the jt. Okay, so the deal with e to the jt is at the top right, you have to differentiate e to the lambda t with respect to lambda. So therefore, the t is now being chain root down. Okay, differentiate lambda t with respect to lambda, you get t. So therefore, top right, you're going to get t e lambda t. So this guy is d lambda, e to the lambda t. Okay, so not to worry it is always t e lambda t basically. So it's a very standard solution form. Okay, so this will be for the particular solution if you can plug in the x1 and x2 not. But if let's say they never give you the particular, they never give you the initial conditions, then you can only write down the general solution. So general solution means this x1 and x2 not, right, they are values that you do not know. But you know they are constants. So if you have a constant vector times a constant matrix, then this is just a bunch of constants. Okay, constant matrix times constant vector, right, you get a constant vector. So therefore, this is your vector C. So it's just a constant vector, arbitrary constant vector. Okay, because P inverse times x0 equals to that constant vector. So therefore, if you are to write down the general solution, it will be just P e to the dt times the constant vector C, like C1, C2 Any questions with that? Because sometimes they don't give you the initial conditions, so you're expected to produce the general solutions which contain constants. Yes? Okay, good. So now we are going to solve this as an example. So you can see that x prime and y prime, right? So the matrix notation will be x prime y prime, then equals to the matrix A, which is 7, 3, 2, 2, then times the function vector xy. So of course, the prime vector must be the same order as the function vector. Okay, you don't put like x prime, y prime, then you put yx, then in trouble. Okay, so therefore this guy, right, is going to be 7322, as you can see the coefficients right there. Okay, initial condition is given. So therefore this is your matrix A. So because in the solution we will need our eigenvalues and vectors. So therefore you have to solve for the eigenvalues. Okay, so solving for the eigenvalues, just recap, you get lambda square minus the trace. So the trace is 9 lambda plus the determinant. So determinant of A, right, will be 14 minus 6, right? So that's an 8. Okay, so then this is equivalent to 0. Can solving for eigenvalues. Then in this case you have lambda minus 1 and lambda minus 8. So that you can get a minus 9 here. So therefore you get lambda 1 equals to 1, lambda 2 equals to 8. Okay? Oh, okay. Maybe I switch so that I can get the same form as my solution given there. Of course, if you want to put 1, 8, no problem. Okay? It's just that you might get slightly different answer from mine. Can Yeah, so therefore, once lambda 1 and 2 are found, then you solve for the eigenvectors. Okay, so solve for the eigenvectors DIY lah. I no need to solve, right? Do I need to solve eigenvectors? Yes. So for lambda 1 equals to 8, so your A minus lambda 1I times V1 equals to the 0 vector. So therefore this A minus lambda 1I, you just have to minus 8 to the diagonals. So therefore this will be 7 minus 8, which gives minus 1. 2 minus 8, which gives minus 6 at the diagonal. Then the off diagonals, no change. Then the V1 you want to find, so I just put XY. Then equals to the 0 vector. So you notice that both rows are dependent. So therefore the span will be minus x plus 3y equals to 0. That's the span of your V1. So which means x equals to 3y. So then you can just choose V1. So you just put your y to be 1 then x is 3. So you found V1. So all you need to do is to repeat the same thing for V2, for lambda 2. So if you do lambda 2, it will be 1. So then this thing will change. So if your lambda 2 is 1, then this is lambda 2. So 7 minus 1 will be 6. Then 2 minus 1 will be 1. So once again, dependent rows. So I solve from the second row is faster. So then the answer here will be 2x plus y equals to 0. 2x plus y equals to 0. So then the span must be y equals to minus 2x. So therefore I can choose V2 to be 1, 2. Because x is 1, then y must be 2. So I found my V1 and V2 already. Okay? And because the matrix A is diagonalizable, right? Because algebraic multiplicity equals to geometric multiplicity. Okay? Which means that you get two eigenvectors to span the whole column or row space of A. So therefore, A is diagonalizable. Okay? Because you can write PDP inverse, well, obviously your P is just V1 and V2 concatenated. So you have to use this guy. Okay? Diagonalizable A, right? So therefore, I can simply use the solution right here. Okay? This is the solution. So you notice that your x of t would be, so your p, right? So you can just concatenate v1 and v2. So I'll be having 3, 1 and 1. Wait. I'm missing a minus here. So it should be 1 minus 2 for v2. So therefore I can put 3, 1, 1 minus 2. Then e to the 8t and e to the lambda, e to the t. Then times the P inverse. So P inverse, you're going to invert the matrix P. So it'll be 1 over the determinant, right? Which is minus 6 minus 1. So it's minus 7. Then this guy will be, I forgot. It's minus 3, 2, right? Then minus 1, minus 1. then times the x1 naught and x2 naught. So the initial conditions are given as 2, 3 respectively. Is that right? Huh? V2, why? 1 minus 2, is this one right? Oh, this part is wrong, right? This should be minus 2, 3. Swap, this two swap, right? Is that correct? Yeah, this one throw a minus, right? Then this two swap, right? Correct, so like that should be correct. Yeah, Dawson, your question is? Choose V2, why? Everything okay? Yeah. Okay, so this is the correct form of the solution, but it's not the final form. Not the final form. So by right, you have to multiply out the matrix so that you get two functions of t for x and y. Because you're trying to solve for x of t, y of t, correct? So therefore, in this case, so this x of t, right, is actually your x of t, y of t. So maybe this one I make it clearer. This x is the vector x. By right, it will be x of t, y of t. So therefore, how do you get the functions of t? You have to multiply out everything. Then there's a recommended way to multiply out. You multiply out from the right faster because this is a vector, right? You don't want to do the multiplication of the matrix, which is more tedious. So you do it from the right. So you can see that this is what? This is going to be giving you minus 4 minus 3, so minus 7. Then this is minus 2 plus 9, which is 7. Okay? Then you will multiply to the 1 over minus 7. Then you're going to get, obviously, 1 and minus 1. Then after that, you multiply to the next matrix. So you can see that I'm multiplying from the right. So then this guy will just give you the vector, which is e to the 8t and minus e to the t. Can? Then after that, you multiply by the last matrix at the extreme left. So this one multiply. So then you're going to get the final answer. So this will be 3e 8t minus e to the t. Then the other one will be minus, e to the 8t minus 2, or rather plus 2e t. So this will be the answer. Okay? First row will be x of t. Second row will be y of t. Yes? No, as in the x and y, because you have to look at the original ODE. Yeah. You mean the initial condition? Oh, if you don't put, okay, maybe I think the next example will demonstrate that. Yeah, next example will demonstrate the one without initial conditions. Any other questions? So if you have no questions, then we look at the next one. So for the next question, I think I will not solve the eigenvalues and vectors. Or do I need to do it? Okay, so for this second problem, so the matrix A can actually identify from here, right? So this will be x prime y prime equals to 2, 1 minus 1, 4. Okay, this one looks familiar. So I think 2, 1 minus 1, 4 is not diagonalizable. Let me see if I have solved this before in topic 2. So I need not do it again. Hold on. I might have done it in topic. There, 2, 1 minus 1, 4. Okay. So the eigenvectors will be 1, 1 and 0, 1 respectively. Okay. So I straight away use or do I need to solve for the generalized eigenvectors with you? So this is matrix A. So once again, you need to solve your eigenvalues. So it'll be lambda square minus 6 lambda. Then this is what? 8 plus 1. So it's plus 9. So therefore this will be lambda minus 3 square. So then you have a repeated eigenvalue. Lambda 1, 2 is 3. Okay, so this one is the algebraic multiplicity equals to 2 because of the square here. So then you want to solve for the eigenvectors, right? Because you have only one eigenvalue. So your A minus lambda I times your V1 equals to the 0 vector. Okay, so maybe we straight away write. So this one will be 2 minus 3, which is minus 1. 4 minus 3 is 1. So you can see both rows are dependent. So therefore, you're going to get x equals to y. Right? The span will be minus x plus y equals to 0. So it's x equals to y. Then it means to say that your V1, right, is 1, 1. So which means to say that the AM is 2, but the GM is 1, because you only have one eigenvector for this span. The span is a line. So the geometric multiplicity is 1. Okay? Since eigenspace is line. So the line is x equals to y. Okay? Y equals to x, which is a diagonal 45 degrees line. So you are lacking in one eigenvector. So therefore you have to solve for the generalized eigenvector. Need generalized eigenvector. So you just solve for the same A minus lambda I times V2 equals to V1. So this one is V2 then. So this one will be 1, 1. I mean, that's how you solve for the generalized eigenvectors. Right? So then now this one is minus x plus y equals to 1. So the span is y equals to x plus 1. Okay? So y equals to x plus 1, you can choose x to be 0, conveniently, and y will be 1, because 0 plus 1. So you found your generalized eigenvector. Is that right? So that I think that's a recap of what we have gone through in topic 3. So, because matrix A cannot diagonalize, okay? Matrix A cannot diagonalize, right? So therefore, we will need the Jordan decomposition form of the solution. Can? So we need this guy. Okay? But because you got no initial conditions given. So therefore, you just multiply these two together. Becomes C. Because matrix times constant vector. Constant matrix times constant vector, right? Is just a constant vector. Okay? So therefore, what's the solution? So the solution is x of t, y of t. So your P must be V1, which is 1, 1. And then V2, just now we found it to be 0, 1. Okay? So there will be 0, 1. Then e to the 3t at the diagonal. Then the off diagonal must be t e 3t. Must follow this form lah. Then the constant vector, you just put C1, C2 because got two constants of integration in the general solution. Is that okay? So then, to get the final solution, you just do the same thing. Multiply from the right. Cause got vector easier to multiply. So it'll be C1E3T plus C2TE3T. Then the second row will be just C2E3T. Then after you multiply by the first matrix to the vector here. So therefore your final answer is this first row. Then the second row is just this times this first row. But you also have a C2 term. So the C2 will be plus C2 E3T. Is that right? Okay. So if you want to simplify by factorizing out the common terms, it will be e to the 3t multiplied by C1 plus C2t. Then the second row will be C1 plus C2 plus C2t. So this will be the solution. Any questions? Yeah, got. But depends on what is the mistake you make. If your vector use different, okay what? As long as the span is correct. Oh, that means it's a wrong span, wrong vector lah. Yeah, got error carry forward. Yeah. You can leave it here, but you'll get some marks deducted. Maybe like 1. You got time, then you just expand all. But if no time, you just leave it like that. Then say, okay, then just put like answer. Then can move on to the other questions. I think 1 mark gone. Because this is the solution already, what? Then the rest is multiply only. Any other questions? If no questions, good time to take a break. Yeah. C2T. This one? C2 is just constant, what? C2 times this one, what's wrong? TC2e to the 3t. Can? Right. So let's continue. And having gone through the examples where we use the blue boxes, general formulas for the solutions, pertaining to whether your matrix A can be diagonalized. Now we apply to this math modeling problem. So recall that initially we have our heat transfer problem, which is between a plate, a hot plate, and air, right, in a room. So therefore we end up with these two ODEs that are coupled. So therefore now we have to solve the system, right, for the general solution. Okay? Yeah, so the ODE system is TP prime, TA prime. Let's write down in the matrix notation to identify our matrix A. So your coefficient matrix must be minus RP. Then the other one will be RP. Then the bottom row will be, as you can see from here, RA. And then the RA times minus will be minus RA here. So therefore, this guy is your matrix A. And you multiply to the function vector TPTA. Okay? So no need to expand the RP and RA. They are just bunch of constants. So this will be your matrix A. Now you have to find the eigenvalues of matrix A. So in symbolic form, we can also find the eigenvalues. So therefore, lambda square minus the trace. But the trace is just, okay, so you can see the minus, right, for both terms. So you factorize out the minus, so minus minus become plus. Then the bracket will be RP plus RA times lambda plus the determinant. So determinant is RP times RA minus RP times RA. So actually the determinant is 0 for matrix A. So therefore from here you notice that you can factorize out lambda. So you get lambda plus RP plus RA equals to 0. So that means your lambda 1 is 0. Then your lambda 2 is just minus of RP plus RA. So you found the eigenvalues already. And you got 2 eigenvalues. And you need to solve for the 2 eigenvectors if available. So now let's look at lambda 1. So for lambda 1 equals to 0, so your A minus lambda 1I will be just the same matrix A, right? Same matrix A, because you minus 0. So that's not doing anything. Then times the vector xy equals to the 0 vector. So you notice that both rows are dependent. Okay? The reason is because, right, this is RP, or rather this is minus RP, RP. This is RA minus RA. So if you solve from any of the rows, you will be able to divide the RA off. So effectively, you get, let's say, RAX minus RAY equals to 0. But that's just saying that you have y equals to x, because you divide by RA throughout. Okay, so both rows are actually dependent. So if y equals to x, that means your v1 is just 1, 1. Okay, so you found the eigenvector v1. So next, for lambda 2 equals to this minus of RP plus RA. So you do the same thing. So your A minus lambda 2I is times V2. Oh, hold on. This one I forgot to put a V1. So therefore, this guy will be equivalent to what? So you can see that this is minus RP, right? Minus RP, then you minus minus. So you plus RP. Can minus minus. So the RP cancels off. You're only left with positive RA. Okay? So therefore, this will be RA, RP. Then the other row, right? This will be RA. Then this is minus RA. So you notice that if this is minus RA, right? You have minus RA minus minus RA. So plus RA. So then you're left with plus RP. So once again, you got dependent rows again, which are exactly the same. So hence you have any row giving you RAX plus RPY equals to 0. So therefore you can write this as y equals to minus of RA over RP times y. Oh, sorry, times x. So therefore, you can choose the v2 already. So v2, you can put x as 1, and then y will be just minus RA over RP. Okay? Of course, if you don't like this, doesn't matter, you can put x as RP also. If you have x as RP, then clearly y must be minus RA. Okay? But it doesn't matter which one you choose. You will still get the same answer as what I have here. So you notice that matrix A is diagonalizable because you got two vectors, two eigenvectors. Okay? So if matrix A is diagonalizable, you have to use the one that is using eigen decomposition. Right? So let me just go back and get the solution. Alright? So therefore our solution, oh okay, so we are supposed to solve for the general solution first. Okay? Diagonalizable. So for the general solution, right, we just group the two matrices together because this one not given yet. So we just say that this is C1, C2. So therefore our temperature solution, T1, TP. So TP of T, the temperature of the air, TA of T. So your P, right, must be V1, V2, but your V1 is just 1, 1. Then your V2, right, is 1 minus RA over RP times e to the 0t, e to the 0t. But e to the 0t is e to the 0, so therefore that's 1. Then e to the lambda 2, but lambda 2 is this guy. So it must be e to the minus of RP plus RA t. Then after that you multiply by C1, C2. Okay? So it's working out the general solution here. So therefore, if you multiply this, then that's going to give you your solution form. So if you multiply this, so you notice that it's just C1 here, and then it's just C2 times the second term. Okay? Then if you multiply again, so you're going to get the answers given, the general solutions given. So it'll be C1 plus C2 e to the minus RP plus RAT right here. And then the second row will be 1 minus. So sorry, C1 minus RA over RP times C2, then with the exponential term. So this will be your general solution. Any objections? So after we get the general solutions, we can solve for the particular solution either by using the same stuff here, or you can solve for C1 and C2 by applying initial conditions. Either you can use this, or you can apply initial conditions to find C1, C2. Okay? So that will be the gist for the next part. So you can see that if you have initial conditions that are given, right, then you can actually solve the C1, C2 and find that they are giving these forms. Okay? So let me just copy and paste. This is our general solution. So hence, if you apply initial conditions, apply initial conditions. So that means your TP0 and TA0, TP0 and TA0. So you apply in vector form. So this T must be 0. So if this T is 0, right, that means this thing will be 1. This thing is 0. Okay? So therefore you get C1 plus C2. Then the second row you get C1 plus RA over RP times C2. But this guy is equivalent to TP0 and TA0. Is that right? So therefore, how can you solve this? If they ask you to solve for C1 and C2 explicitly, then you just solve system of linear equations. So therefore, you have something like R1 and R2. So this one will go back to topic 1. So therefore, you have Gaussian elimination. So hence, you can solve by, for example, R2 minus R1 or R1 minus R2, doesn't matter. So if I do R1 minus R2, Then you have the C1 cancel off exactly. Can ah? So therefore from here you're going to have C2 times 1 minus RA over RP. Then that's equivalent to TP naught minus TA naught. Is that right? So then you want C2 what? So C2 will be giving you this TP naught over TA naught. TP naught minus TA naught divided by this 1 minus term. Okay, I noticed that I have a plus here. Why is it plus? Did I messed up? It's a plus. Okay, so this one is a minus here. So if it's a minus here, right? Hey, wait a minute. Did I mess up? Sorry, this should be a minus. My bad. This guy should be a minus. Okay, there's a minus here. So this is a minus here. So minus here, R1 minus R2. This one will be a plus. So it should be 1 plus RA over RP. Okay? Yep. So therefore you got C2 already. If you have C2, then you can solve from R1 your C1 then. C1 is just TP naught minus C2. Okay? So therefore you can see the answer here. So you found C1 and C2. So this one just solving simultaneous equations. Is that right? Hence, you have the particular solution solved as well, because you just sub C1 and C2 into your general solution, then actually your particular solution is complete. Okay? Yeah, so therefore we can actually graph our temperature functions already. So let me show you the temperature function and then also verify what I think Naya mentioned, right? You are going to get a convergent temperature function. Okay? So these are the parameter values that I have given here. Can you see? Right? U equals to 500 watts per meter squared dot Kelvin, the area, the mass of the plate, the heat capacity of the plate, the mass of the air, and the heat capacity of the air, the initial temperature of the plate, 900 degrees Celsius, as well as the temperature of the air, initial temperature of the air. So once you put in the parameter values into decimals, as you can see, and then you define what is your RP and RA, UA over MC, put in the initial conditions, and put in the constants, C1 and C2, as we have solved them. Then put in your solution, your temperature solution functions. Okay? So you can clearly see that the air starts from 30 degrees Celsius. Right? That's the initial temperature that you give it. Then the plate starts at 900 degrees Celsius. That's the initial condition that you gave. So therefore what's going to happen is that the temperature is going to, the plate is going to lose heat, right? Because cooling air is going to remove heat from the plate. So the temperature decreases, 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 and then the air gets heated up, heated up, heated up, heated up, right? And eventually they are going to reach a steady temperature of around 733 degrees Celsius. Can you see that? Okay? Right? So certainly you can mess around with the parameter values, right, to see what influences the solution graph in whatever way. So one of the interesting maybe observations will be, if you were to decrease the heat transfer coefficient between the heat and the between the plate and the air, you will be expecting to see what? To see the convergence of the temperatures taking longer time. Okay, so if you decrease heat transfer coefficient between the two bodies, so you can see, right? The convergence of the temperature towards the same constant temperature will take longer time. Okay, can you see? Right? And then you can of course mess around with other parameters as well. What do you think will happen if I increase the mass of the air inside the room? So that means I put the plate in a bigger room. Any guesses? If I increase this mass of the air, right, the cool medium, what do you think is going to happen to the graph? Then? Yeah, one thing is it take a longer time to converge. Yeah, correct. Because, I don't know, it feels correct. Because you have more air to heat up now. But if you have more air to heat up, that means you have more cold medium or cool medium inside the room. So what do you think influences the steady temperature? Go up or down? Correct. So let's increase the temperature, let's increase the mass of the air inside the room. Okay, see? So what Xavier mentioned is correct. It takes longer time to reach the equilibrium, but it is also residing at a lower uniform temperature. Okay? Because you got more cold stuff inside the room or more cool stuff inside the room. So therefore it is only logical that the equilibrium temperature wouldn't be that high. Can? Okay? So therefore I hope the analysis makes sense to you. Any questions? Yes. For the plate and for the air. You will move up lah. You will move up the equilibrium temperature. Yeah, correct. So if you increase the mass of the plate, right, it's going to move the equilibrium temperature up. So you can see that originally it's 1000, right? Then if you increase the mass of the plate, you can see that the equilibrium temperature is going to be higher. Any other questions? Okay. So I don't know if you guys realize that this is actually a very high temperature, 700 plus degrees Celsius. Okay. So it is not safe if you have an enclosed room with a hot plate that is of 1000 kilograms, right? That is going to make the room super hot. So it's like an oven. Okay? This thing is like an oven. Right? Very dangerous. Alright? Okay, so I'm going to stop the lesson here and we will look at the inhomogeneous systems with excitation later during lecture. So now I'm going to mark attendance. I think Alexander not here yet, right? I thought you just arrived. So you attend the following class, right? I don't remember seeing you that early. Yeah. Okay. Maybe my memory. Earlier is not here. Emelina, Angelico, Jiashon, Brian. I think Brian is here. Chen Chang not here. Zhen Yi not here. Ivan is here, right? Ivan. Di Yang not here. Emilia not here. Erwin not here. Yan Jin, Zhan Yang, Dong Bing, Noritetsu. Next lesson. Then I mark you first. Javier is here. Joey not here. Jordan is here. Kayla is here. Kevin not here yet. Ken Leong, Chara not here. Dawson here. Chen Ying not here, right? Jonathan, Kun Yong, Mac not here. Mikhail, Mohan, Azari, Danish is here. Irfan, Naya is here. Bing Jie not here. Geng Hong, Zixuan, Fadila, Phoebe not here. Yan Heng, She Yun not here. Benjamin, Raymond, Reese, Rujiratanalai, Jumpang, Jerome, Sean, Brian, Justin, Hao Po, Ryan, Suhadi, Johans, Wei Yan, Yi Zhong, okay. Tiamzhen, Trisha, Yang Hong, Shi Kang, Xing Zhi, Zotet, Zun Ping Wai. Okay. Yep, so I will end the class now. If you want to stay for the second lesson, you can. I'll just be going through the same thing.